Dear students, here we will discuss about the Hund's rule. And Hund's rule tells us that how the electron are filled according to the energy in the orbitals. And so this rule is also called as the Hund's rules of maximum multiplicity. Hund's rule of maximum multiplicity. So here we will see that why it is called as the Hund's rules of the maximum multiplicity. Hund's rule is based on the observation of atomic spectra. Its bases are the atomic spectra of atomic spectra of the atoms and the molecules, which is used to predict the ground state of an atom. So how we can state the Hund rules? We can state the Hund rules as for a given electron, for a given electron configuration, the lowest energy, the lowest energy electron is the one. Which will be the lowest energy electron? The lowest energy electron is the one with greater value of multiplicity. With greatest value of multiplicity. So the electron which have the greater value of multiplicity will be the electron of lower energy. So this is the Hund rule. It is also called as the Hund rules of maximum multiplicity. That is the electron which has the greatest value of the spin multiplicity. That is, here we can write the spin multiplicity. So the electron with the greatest value of spin multiplicity have the lowest energy. So it will go to the cell orbital which has the lowest energy. So this implies that if two or more orbitals of equal energy are available, the electron will occupy them singly. So here we can understand it by the quantum number. As you know that we have the principal quantum number, we have orbital quantum number, and then we have magnetic quantum number, and then we have the magnetic spin quantum number. So here n represents the value of k, l, m, and so principal shells k corresponds to the 1, L2, M3 and 4 and so on. And L represents the value of subshell, that is 0, 1, 2, 3, that corresponds to the S, P, D, F, and these are the subshells. And these are the principal shells, and L which is the orbital quantum number which represents the subshells, and ML which is called as the magnetic orbital quantum number. Here its values are for n is equals to 1, L is equals to 0, its value can be the 0, plus minus 1, plus minus 2, plus minus 3, up to so on, plus minus L, and MS has the values according to the spin plus 1 half, or it can be the minus half. So for here we can see that, for example, for any atom for which n is equals to 1, for any shell, for k shell, for n is equals to 1, value of L can be equals to 0. But for n is equals to 2, the value of L equals to L has the value of 0 and 1, and for n is equals to for this one n is equals to 2, Value of L is the 0, 1. 0 states corresponds to the S and it corresponds to the P state. Here for n is equals to 1 we have only subshell which is the 1s substate. For here we have the 2s and 2p substate as well. And for L is equals to 0, value of ml can be the 0, it can be the plus 1 or it can be the minus 1. So ml basically it represents the orientation of angular momenta, and it defines the orientation of orbital angular momentum states. So there are for for L is equals to 1 we have three possible value of ml. For L is equals to 1 it can be the 0, it can be plus 1 or it can be the minus 1 orientation. So these are the orbitals. And we can, according to the Pauli exclusion principle, we can say that there can be the maximum number of two electron with a different set of quantum number can occupy the same quantum states. So here we can say that if the two or more orbital of same energies are available, for example for L is equals to 1 ml has the value 0, plus 1 and minus 1. So we have three orbital with the same energy are available here. So first they will be occupied singly. So here it means that first electron will go to the, we can say that this is the PC, this one is the PX and this one is the PY state. First electron will be filled singly with the spin up state. So electron first will go to the PZ state, then PX and then PY state, and then after filling these orbitals singly, then they will be occupied with the spin down state. So this is the Hund rules, which basically tells us about the filling of electron, that if there are two or more orbital or of equal energy are available, then the electron first will go to the first will occupy them singly with the spin up state and then will go to fill them with the spin down state. So this rule was discovered by the Friedrich Hunds in 1925. So that's why it is called as the Hund's rules of multiplicity. Now we are going to explain the multiplicity, that is what is the multiplicity of the states. Here the multiplicity of states. Here as we are talking again and again in the Hund rules about the multiplicity of the states. Now what is the multiplicity of state in atom? In atom the multiplicity of the state is 2s plus 1. Now here what is the S? S is the total electron spin. It represents total electron spin. And so this is the total electron spin. So high multiplicity state, our greatest multiplicity state is therefore the one which is with the high spin state. Which one is the greatest multiplicity state? The greatest or larger multiplicity state will be the one multiplicity state is the one with the which has the high spin state. Now here what is mean by high spin state? For example, if we have the three orbital of the same energy and all have the electron with the same spin, that is all are in the spin up state. So this is called as the high spin state. For example, if we have the state like this one, we have the shell like electrons like this one, then this will be the low spin state. So if the all electron in the all orbitals are in the same spin state, then this is called as the high spin state. And if the electron are in opposite with the opposite spin state, then this will be the low spin state. So the state with the highest multiplicity is that state which is high spin state. High spin state is actually the greatest multiplicity state. So it is the lowest energy state. It is greatest multiplicity state corresponds to the lower energy state. It has the lowest energy. Why it has the lowest energy? Because it has the tendency for the other electron. We need to fill the more electron in order to stabilize the atom. So these are the lowest. This is also called as the lowest energy state. So high spin state is which has the greatest multiplicity. It has the lowest energy. So electron, according to the Hund rules, will go to these states. And so since the spin state of each electron is spin of each electron is 1 by 2, so each electron has the spin half. So the total spin of the electron is can be represented by total spin of the electron is 1/2 of the total number of unpaired unpaired electron. So for example, if we can say that, and multiplicity corresponds to the 2s plus 1. So for example, for the nitrogen, so here we can write it like example. This is an example. Nitrogen, it has a ground state. Its ground state which has the 3 unpaired electron. There are the 3 unpaired electron in the ground state of nitrogen. So what will be its total spin? Total spin for this one can be calculated. Total spin S for this will be equals to 1 by 2 into total number of 3 unpaired electrons. So it has the total spin of 3 by 2. And what will be the multiplicity? Multiplicity, which is equals to 2s plus 1. So multiplicity is the 2 into 3 by 2 plus 1, and it will be equals to 4. So this state, ground state of nitrogen, which has the 3 unpaired electron, it has the multiplicity of 4 and total spin of 3 by 2. So now we will explain that how these high spin state and lower energy state related to the stability of an atom. So here, for example, in the quantum mechanics, in case of quantum mechanics, here in quantum mechanics, with accurate wave function, we can say that the said to be said that for increased stability is the decreasing in, is related to the screening effect. So increased stability of an atom, stability of atom related to the screening effect. Now how we can relate it to the screening effect? As we know that the lower the energy and increased stability of the atom rises, because high spin state has the unpaired electron. High spin state here again means that the greatest multiplicity state has the high unpaired electron. All are of parallel spin, and so which must be in the different spatial orbital. And we know that increased stability is related to the decrease in the screening of electron, and here the screening effect is related to the interaction of electron and nucleus. So screening effect here is that the outermost electron or have the less nuclear interaction, or on the less nuclear interaction, feel the less nuclear interaction as compared to the core electron. So this here, when we reduce the screening effect, um, then it increase the stability. How it will increase the stability? Because in the high spin state we have the unpaired electron, so unpaired electron can approach the nucleus more closely, and the electron nuclear interaction is increased. As a result, the screening effect decreases. So as a result of Hund rules, the constraints are placed on the way of atomic orbitals. How we can fill the atomic orbitals according to the Hund rules, and so there are two rules according to which we can fill the electron. So the first rule is that before any two electrons occupy an orbital, occupy an orbital uh, in the subshell, in subshell, the orbital in the same subshell, the orbital in the same subshell will have the parallel spin, will have the parallel spin. So this is the first rule. So it means that first, for example, there are the three orbitals. First electron will be filled with the parallel spin, and then the same orbital will be filled with the opposite spin. Okay, so before any two electrons occupy an orbital in the subshell, the orbital in the same subshell will have the parallel spin. So there should be the parallel, first will be filled with the parallel spin, and then they will be filled doubly before. So second rule is that the first electron will be filled parallel and then anti-parallel. So this is the second rule. First electron will be filled parallel, will be filled parallel, and then will be filled anti-parallel. Anti-parallel. So these are the two rules according to which we can fill the electron according to the Hund rules. So here, for example, we have the few examples here to understand the Hund rules. For example, we have the boron. Is here we can write the element, here atomic number, here we can write this atomic number, and then configuration, and then spin of p electron. Here we consider only the spin p subshell, so spin of p electron according to Hund rules. So first we have the boron, its atomic number is 5, and then we have the carbon and its atomic number is 6, and then we have the nitrogen with the 7, oxygen with atomic number 8, and then we have the fluorine, then with the atomic number 9, and then we have neon with the atomic number 10. Now we can write the electronic configuration. So there boron has the electronic configuration 1s2, 2s2, and then 2p1. So carbon has the electronic configuration 1s2, 2s2, and 2p2. Nitrogen 1s2, 2s2, 2p3, and oxygen 1s2, 2s2, and 2p4. And fluorine has electronic configuration 1s2, 2s2, and 2p5. So electron we are adding the electron in the p orbital, and so for the neon, which is the noble gas, noble elements, here the electronic configuration is 2p6. So here the p shell is fully occupied, so with the 6 electron. Now how we can fill the electron according to the Hund rules. So according to the Hund rules, for the p, which is the valence shell, here the electron, here we have only 1 electron. For this carbon, here the 2 electron in the p subshell, so first they will be filled singly. Here you know that this one is the, for example, pz, this one is the py, this one is the px, so here will be the no electron. So for the nitrogen, for air, electron first will be occupied singly. Now all three p orbital, pz, py, and the px are occupied singly. And now what will happen to the next electron, which in the case of fluorine, which has the atomic number 9, for which we have the 2p5 electron. So here in this case, again we have pz, py, px orbitals. So first electron will occupy singly, and then the next electron will go to here in this state. So here for oxygen atom, as it has the 2p4 electron, first electron will be occupied singly, and fourth electron will go into the pz. And for fluorine, the fourth electron will be go to the pz state, and then in the py state will the fifth electron. And for neon, which has all filled p subshells, so here the electron will be filled according to the Hund rules. First they will occupy with the parallel spin, and then will occupy electron will go with the anti-parallel spins. So this is the filling of orbital according to the Hund rules. So Hund rules, in this way we can relate it to the stability. We have learned that how we can relate it to the stability, how we can relate the high spin state of higher multiplicity, that how it decreases screening effect. And so this was all about the Hund rules. Thanks for watching. For more videos, please subscribe our channel.